And topics today is about the machine learning enhanced algorithm for the optimal landing problems. This is a joint work with Long from Princeton University, and Zhang from Peking University, Hu from Princeton University, and Professor Awena from Peking University and Princeton University, and Han Zhiqing from Flatland Institute. This is the contents of this talk. This talk includes 5 parts. The first part is about the background of the talk today, where we will introduce the optimal landing problem. In the second part, I will introduce the 2 points boundary value problems for the optimal landing problem. In third part, I will introduce the proposed machine learning enhanced algorithms for solving the 2 points boundary value problems in the second part. We will also introduce some experiment results in the fourth part. Finally, I will make a conclusion of today's talk. First, let's go to the background of this talk today. In this slide, we can see there are 2 images. The first image is about a real core router, and the second image is a system of the core router. As we can see from the first image, the core router has 4 routers. The routers in the diagram usually routed in the same direction, and the other routers usually routed in the opposite direction. Usually, there are 2 coordinates used to describe the dynamic of the core router: the body coordinate and the world coordinate. The position and the angle of the core router usually described in the body coordinate. The linear acceleration and the linear velocity and the angular velocity usually described in the world coordinate. The rotate speed of these 4 rotors controls the locomotion of the core rotor. So we then describe the dynamic of the core rotor in the format of mathematics. Here there are 4 equations to describe the dynamic of the core rotor. The first equation describes the position of the dynamic of the core rotor. The second one describes the linear velocity of the core rotor, and the third one describes the angle of the core rotor, and the last one describes the angular velocity in the body frames. In the first equation and the third equation, the matrix capital R transpose and matrix K in the third equation. There are 2 transformation matrices from the body frames to the world frame. We denote the dynamics of equation 1 as the following simplified forms. That is, the dot of the state x equals the function f of the state x and the control u. The state x has 4 terms. The first term p is the position, and the second term vb is the linear velocity of the core rotor, and the third term is it, which indicates the attitude of the core rotor, and the last terms omega b indicates the angular velocity. Also, the control u also has 2 terms, with the first term capital Tu is the total thrust, and the second terms tau u, which indicates the torque of the core rotor. We then introduce the problem definition of the optimal landing problem. The optimal landing problem is to find the optimal control u star to steer the core rotor from an initial state x0 to a target origin 0 with the minimal control effort and the shortest landing times. So we consider the following optimal control problem with free terminal time. In this problem, we are going to minimize a cost function, objective function C with respect to the dynamic of the core rotor. The objective function C is a function of the state x, the control u, and the optimal landing times Tf. It has 2 parts. The first part indicates the landing time, and the second part is the accumulation of the weighted division between the control u and the reference control ud. The reference control ud has these forms that used to balance the gravity, and the weighted matrix capital U used to characterizing the cost of the division from the reference control. With this optimal control problems, we are going to introduce the 2-point boundary value problems for this optimal landing problem. But before we introduce the 2-point boundary value problems, we need some modification of the original optimal landing problem. To do that, we consider the TF as a new state xn plus 1 and introduce a new variable tau, which equals the division between T and TF. We then have the dot of the new state xn plus 1 equals 0. So the dynamics, the original dynamics will become the following equation of 4. We denote the x tilde and the u tilde with these two forms respectively. Then the simplified dynamics 2 will become the following form. Also, we replace the integral variable with tau, and the cost function will have the following forms. Therefore, the optimal control problem 3 can be reformulated as the following problem 6. The problem 6 has the advantage of fixed terminal times, that is the tau equals to 1, and also the objective function has a fixed upper integral limit. So this is the motivation we made this modification for the problem. Now we introduce the Pontryagin minimal principle, with which we use to derive the 2-point boundary value problems for the optimal landing problem 6. According to the Pontryagin minimal principle, the necessary condition for the optimality of the problem 6 are the following ordinary differential equation 7, together with two boundary conditions augmented with this transversality condition, where the tilde of lambda is the co-state and the capital H is the Hamiltonian, which has the following form. In the ordinary differential 7, the optimal control U tilde star can be obtained by minimize the Hamiltonian with respect to the U tilde. So with the equation 7 to 9, the 2-point boundary value problems for the control problem 6 can be written as the following forms 10. Therefore, we can solve the 2-point boundary value problems 10 to determine the solution of the original optimal control problem 6. However, the 2-point boundary value problems is not easy to solve. So why the 2-point boundary value problem is difficult to solve? There are many two reasons. The first reason is that the 2-point boundary value problem has a high dimension. The second reason, which also the most crucial reason, is that the 2-point boundary value problems is highly depends on the initial guesses. In table 1 is the solving of the 2-point boundary value problem corresponding to the free terminal time problem with zero initialization. In the first line of the table 1 is different initial guess of the optimal landing test TF, and the second line is a success rate we obtained in different cases. As we can see that in all cases, the success rate for solving the 2-point boundary value problem directly is very low. So this is the motivation we propose the machine learning enhanced algorithm. Before we introduce the proposed machine learning enhanced algorithm, let's look at the fact that the solution of the free terminal time problem is also the solution of a corresponding fixed terminal time problem. To the fixed terminal time TF equals the optimal terminal times TF star. This can be seen from the figure 2. Figure 2 shows the solution of position obtained by the free terminal time problem and that of the corresponding fixed time problems with the terminal time is TF star. From this figure, we can see that the solution of position obtained by these two methods are exactly the same. So based on this fact, we can propose the following algorithms to solve the free terminal time problem. This algorithm, which calls the warm star with fixed terminal time solution, given an initial state x0, and the initial guess of the optimal terminal times TF started. We first solve the fixed time problem with the fixed time equals the initial guess of the optimal landing times TF started, and then using the zero initialization to solve this fixed terminal time problem. In the third steps, we solve the free terminal time problem by using the solution from the step 2 as the initial guess. And finally, we get the solution of the free terminal time problem. The performance of the performance of using the algorithm 1 to solve the free terminal time problems was shown in figure 3. In this figure, the x-axis indicates different choice of the initial guess of the optimal terminal time TF star, and the y-axis indicates the success rate obtained by using the algorithm 1 to solve the free terminal time problem. In this figure, the bar in dark color indicates the success rate for solving the free terminal time problem, and the dot in light color indicates that the success rate for solving the fixed time problems, but the free terminal time problems failed. So the sum of these two parts is the success rate of solving the fixed terminal time problem. This indicates why the success rate for solving the free terminal time problem is always less than the success rate of solving the free terminal time problem. There are another information we can see from this figure that the success rate of solving the original free terminal time problems get improved. However, this result is still far from good. So we want to improve the success rate of both solving the free terminal time problems and the fixed terminal time problems. A straightforward is to propose some techniques to improve the solving of the fixed terminal time problem. So that's why we propose the space matching method for solving the fixed terminal time problem. The space matching method can be represented by the following process. To make it clear, I draw the figure in the right. In this figure, the x0 is the initial state and the orange 0 is the target state. The space matching method first select k-1 loads on these parts, and we denote these loads as x0 k-1, x0 k-2, and so on, based on the distance from the initial state. So this process starts by solving a fixed time problem, which takes the x01 as the initial state and the x00 as the terminal state, and takes the TF started as the fixed time. After this problem has been solved, we use the solution as the initialization for another fixed terminal time problem, which takes x0 as the initial guess and the x00 as a target state. After this problem has been solved, we repeat this process until the step reach capital K. That is, the initial of the state is exactly the original problem. Then the fixed time problems will be solved. Based on the space matching method, we propose the algorithm 2 to solve the free terminal time problem. This algorithm, which called the worm star with the fixed terminal time solution through space matching. The basic idea behind this algorithm is that we first use the space matching method to solve the fixed terminal time problem. Then we use the solution of the fixed terminal time problems to be as the initial guess for solving the free terminal time problem. The performance of using the algorithm 2 to solve the free terminal time problems are shown in the figure 4. This figure is about the warm star with fixed thermal time solution through space matching. The x-axis of this figure is the different choice of the initial gas for the optimal landing times TF star. The left y-axis indicates the success rate, and the right y-axis indicates the computation times. There are bars and lines in different color, which indicates different choice of the space matching step. From this figure, we can see many information. The first information is that with the algorithm 2, the success rate of solving the free terminal time problem and the fixed terminal time problems are get improved significantly, which shows the efficiency of the algorithm 2. The second information we can see from this figure is that if the space matching step capital K equals to 60, and the initial gas of the optimal landing time TF star chosen as 20, we get the relatively best performance. The third information that we can obtain from this figure is that if the initial gas of the optimal landing time TF chosen as 4, we will get very poor performance. This indicates that a good choice of the initial gas of the optimal landing time will play an important role in solving the free terminal time problem. So we draw the distribution of the optimal landing times TF star obtained by solving 300 optimal landing problems with randomly selected initial state. In the figure 5, we can see that the TF star distributes in a wide range, which indicates that a good choice of TF star will also play an important role in solving the free terminal time problem. Considering all above, we propose the machine learning enhanced algorithm to solve the free terminal time problem. The proposed method mainly contains 3 steps. In the first step, we use our deep neural networks to learn the relationship between the initial state x0 and the optimal landing times TF star. So we can use the deep neural networks to make a prediction of the optimal landing times TF star first. And then we solve the fixed terminal time problem with algorithm 2, where the gas of the terminal time is given by the deep neural networks, and we then obtain its solution and denote it as the x fix. In the last step, we use the x fix as the initialization for solving the free terminal time problem. Here we show the performance of the proposed machine learning enhanced algorithm. In the figure 6, this is a comparison between the constant linear model and the neural networks model when they are used to predict the optimal landing times TF star as the initial gas in the 2-point boundary value problem solver. In this figure, the x-axis indicates the different choice of the matching step, and the y-axis in the left indicates the success rate, and the y-axis in the right indicates the computation time. From this figure, we can see that in all cases, the proposed method always obtains the best performance. And when the space matching step chosen as k equals 60, the proposed method performs the best. This figure shows the efficiency of the proposed method. We then going to show some experiments result. First, in table 2 is a summary of the success rate and the computation time of different methods. In this table, the first line is a different setup of different methods, and the second line is the success rate for different methods, and the third line is the computation time obtained by different methods. The first column indicates to solve the to solve the two-point boundary value problems directly with the initial guess of the TF star equaling 8. The second column indicates that to use algorithm 1 to solve the two-point boundary value problems with the initial guess of TF star equaling 16. And the last three methods indicates to solve the Friedman time problems with the proposed algorithm 2 with the matching step equaling 60. The initial guess of the optimal landing times are provided by the constant 16 and a linear model and the neural level model, respectively. The last one indicates the proposed machine learning enhanced algorithm. From this figure, we can see that the proposed method achieves relatively best performance, which indicates the efficiency of the proposed method. We also compare the proposed method to the model predictive control, which is commonly used for the locomotion control of quadrilateral. So figure 7 is the trajectory obtained by the MPC method following the optimal trajectory obtained by the proposed method. The cost obtained by the MPC method is about 32, which is almost double that we obtained by the proposed method, which indicates that the optimality of the proposed method. We also compare the solution obtained by the proposed method and the MPC. Here in the first line of this figure is the position obtained by these two methods. We can see that they are close to each other. However, the angle obtained by the proposed method is more stable than that obtained by the MPC, which indicates that the proposed method is superior. One may ask the question that why don't we use the deep neural networks to provide the initialization directly? This experiment may partially answer this question. In Figure 9, the trajectories on the time interval from time 0 to the time TF star, starting from the same initial state and the following controls provided by different neural networks. The neural networks 1000 indicates that this neural network was trained with 1000 optimal paths. The second one indicates that it was trained with 1500 optimal paths, and the third one indicates that it's trained with 2000 optimal paths. From this figure, we can see that with the increasing of the training data, the performance becomes better. However, the neural networks-based feedback control performs reasonably well at the beginning and then deteriorates. This may indicate that the deep neural networks may not be a good idea. This indicates that to use the deep neural networks to provide the initialization for solving the Friedman time problem directly may not be a good idea. So in the final part, I'm going to conclude the talk today. In this talk, we proposed a machine learning enhanced algorithms for solving the optimal landing problem. First, the proposed algorithm is based on providing a good initialization for the corresponding two-point boundary value problems derived from the Poncharkin minimus principle. And second, the effectiveness of the proposed method was verified through a series of experiments. However, there are still a lot of open problems for future works. The first problem is that how machine learning techniques can enhance direct methods in some similar spirit. And the second work that to be considered in future work is to include the parameters in the dynamic system as the input of the deep neural networks, such that the resulting deep neural networks can deal with various dynamic systems. That is my talk today. Thanks for attention.